Hello everyone and welcome to the Kia Ora Theatre at Linux Conference Australia 2022. First up, we've got Nicolas Dufresne, who is a principal multimedia engineer at Collabora and is actively involved with both the GStreamer and Linux media communities to help create a solid support for codecs on Linux. And he's here to bring WebM Alpha support to GStreamer, introducing video transition retro alpha plane support, a workaround, and we'll dive into the architecture he's implemented to support this kind of video. Now we are going to have time for questions at the end, so put your questions into the questions tab in Venulus as we go, and try to put them in with plenty of time because we are operating on a delay. But yeah, take it away, Nicola.
Thank you, Caitlin. So hello, thanks, thank you very much, LCA team, for organizing this virtual conference. I understand how difficult it can be. It's amazing organization. We have a lot of support, so a big thanks. And it's also part of our effort to not be the problem and solve the problem. So as I got introduced, I'm Nicolas Dufresne. I'm GStreamer contributor. Actually, I've been contributing for over 10 years. I'm quite lucky because I'm allowed to actually contribute to this project in my day-to-day job at Collabora. I've been at Collabora for 11 years now, and I've been able to learn and contribute to so many things, especially nice for someone like me that likes to learn new things. And being a consultant is just about that, jumping into a new project, solving new problems, and getting the job done. And speaking of a job, the implementation of WebM Alpha inside GStreamer was actually mandated by one of our customers in the streaming industry. So they wanted to use GStreamer on some sort of a pro streamer handheld that would basically allow on the road, let's say, more professional streaming capabilities. But one of the big missing features in GStreamer for them was the ability to play back tenures. And then, yeah, but to be honest, I had just no idea what a tenure was. So first thing I did is look at Wikipedia, which says, well, a stinger is an opaque organ or body part found in various animals, typically arthropod, that usually delivers some kind of venom. It wasn't very useful. But after some more research, and because I really wanted to know where that word came from, I actually found that the word tenures is used in American radio station, or was used in an American radio station, as a little sound that would be fairly unique to the station and that would allow the audience to actually recognize the channel that they are listening to. So, and that definition actually, well, it's not really a definition, but that definition actually fits very well to what streamers today actually uses as an audio-video tenure, which is a way to personalize their streaming and their streaming transition, and it could be an entrance, a transition, or an ending, in order to have a very specific signature. So what they are personal animation. For transition, they usually start with a transparent video that transit toward an opaque middle point where the transition take place, and then it would go back to transparent, and then it would go away in the montage. And these are, well, typically authored with tools like After Effects, but it looks like it's feasible these days to make them actually using open source tool. There's a demonstration I've seen recently about producing a stinger with GIMP, Inkscape, and also with Shotcut Video Editor, which natively support with FFmpeg the ability to encode and export those video. The stingers actually could have been in other format than WebM. You could have actually used one of the pro codec like ProRes 444 that has native support for that, or some higher profile in HEVC. But the truth is that it's rarely supported by your hardware. It's not accelerated on everybody's computer. So you need a more expensive setup to use them. And that's where the WebM team, which is a Google team, actually came up with a great idea, which is WebM Alpha. and they actually managed to do that using their royalty-free codec, VP8 and VP9. But there's a but. There's a problem, because neither VP8 or VP9 have support for an alpha channel. They only support 3 channels: the colors, and the 2 chromas, the 2 color plane. The idea they had is that, what if we use 2 streams and we map the alpha from the second stream as we map the luma as from the second stream, the brightness, as the alpha, and then it just ignore the UV plane. And that's exactly what they did. So typically, that's the simplest form, and that's what the software libvpx would produce. VP8 or VP9 decode to 3 planes, the Y, the U, and the V. And then they would decode twice, and then they would map the Y as A. And the X's there are the U and the V, and they are actually set to something uniform, so always the same value, with the idea that during compression, because it's always the same value, it's going to compress very well, so it's not going to introduce as much overhead. This is also a bit unlike if you were to do that with H.264, where you can actually have monochrome encoding. You could have used monochrome encoding instead of this workaround. Now, that by itself is not sufficient. So they actually needed to store and attach the 2 frames together somewhere. And with bitstream like VP8 and VP9, which are they're done, you can't actually extend them. There's no way to add new information to it. So their idea was to use a container format instead. So containers are the name we give to things like WebM, MP4. You'll find transport stream in the broadcast industry, and they would extend WebM, which is a subset of Matroska, which is well known in the multimedia community, in order to support this. Now, what you need to know about WebM to keep things simple, it's implemented on top of an extendable on EBML, which is extendable binary markup language, which what is nice is that you can actually express it in XML in order to represent the content. So to make it short and simplify it a bit, a WebM file is split into 2 groups. The segment is what describes the data that is stored in the container. And then you get the cluster, which has block group and blocks and block additions to actually carry the data that you're streaming. And the way they managed to add this alpha channel, this extra second stream, is through what we call the block addition, which is an abstract piece of binary that you can attach to a frame per frame. And block addition have no meaning unless you actually add a tag in the track entry. So that's what they did. So they added a tag to the video track, which says that we are in alpha mode 1. Why 1? Why not true or false? Because they probably intended to be able to add other modes in the future. I don't see what it would be, but they want to be safe. So whenever alpha mode is set, it means that there's going to be a block addition for each frame, and that this block addition is an alpha channel. So enough of the introduction here. How do we map this into GStreamer? And what I really want to show you is the journey of a GStreamer developer after learning a technology and trying to map it back into GStreamer technology. Just read me well. This is entirely supported in FFmpeg. It has been there for a while. You can both encode and decode in FFmpeg. So we're a bit in a catch-up mode in the GStreamer world in this regard, because we didn't have any use case so far. Actually, that being said, there was prior art, so we'll see later that there was already some work done. We also had to keep in consideration, we had to know actually what we needed to consider before we started. So one of the things I noticed is that non-alpha decoder, the existing VP8 and VP9 decoder, would work just fine, ignoring alpha with a black background. And that should keep working for sure. Another thing, we didn't want to introduce any wrapper for the case where you actually decode VP9 data, because this can be pretty big, 4K, 60 FPS with HDR and everything these days, with Netflix and not Netflix, but with Google YouTube actually using that a lot. It should also work with autoplugger. That what it means is basically it should work in your favorite media player without having to code something. And of course, it should not break the ability to actually disable hardware decoding, which is a relatively new feature, and that would have been very easy to ignore. Now about the prior art. So before I started, just like what I do usually, and I would strongly recommend if you're part of a community, I've talked about the project I wanted to do over the IRC channel of GStreamer, and basically give some layout of the design I would like to use to make sure that I'm not totally off track, that I'm not doing something that would never work. And that was really good because Tim-Philippe Muller and Mathieu Duponchel actually had an old branch which was implementing that for software decoding. There was a bunch of little issues that actually led to not them making it upstream. Basically, it was only software decoder. And anytime you would have actually a hardware decoder in your system, it would actually prefer the hardware decoder over the software decoder, but the hardware decoder might not have alpha support, so that the auto-plugging decision was not correct and was quite surprising. They were also using a feature called QData, which is a basically string identifier for extra data on buffers in GStreamer to store the block addition. I thought it was not very elegant, but it was not a bug. It was fine, but to me, that was not the most elegant way. So I've decided to use a different approach there. But in the end, it was a big time saver because they had solved all the things that I knew the less, which was EBML parsing and handling. So they had the CodecAlphaDemax part in place. All I had to do was to map. So speaking of mapping, so in order to make the codec alpha stream identifiable, I decided to add a new field to the caps that would be exposed by the demuxers. So I would map the alpha mode from the EBML to a GStreamer caps codec alpha. It's a Boolean because I don't believe we will have a new mode in the future. And for the older codecs, they would remain with no fields. This is something that you would have to know if you were to do development in GStreamer, especially regarding the caps, that if a field is not in the caps, it basically mean that it supports any value for other field. And it's nice because in our case, it's a way to not break compatibility. It means that the old decoder will be compatible with the streams that have codec equal alpha set into as a field. If I had created a new format, a new media type, actually like video/x VP9-alpha, I would have broken this implementation. The second part of the mapping was where do we store the block addition. As I said, it was attached to the GST buffer already, so I just keep that. But the way I decided to attach it was to provide in the video library what we call a GST meta, which is a little object that we can attach to every buffer in order to carry some extra data. And that meta, which is called GST video codec alpha meta, actually will hold a reference to the GST buffer that represents the alpha channel. Now, we got the mapping, and how do we process this in order to decode? So my main idea was to avoid actually modifying the VP9 decoders to support alpha. The reason is that, well, the prior art from Tim and Mathieu was done this way, and it would highly increase the complexity of the decoders, and I really didn't want that. And GStreamer is a very powerful graph processing tool, and I thought that, hey, we should create a graph for it. So that's what that was my draft, actually, which I kept till the end, except I renamed a few things. Well, that's the final name, sorry. So basically, to support this new graph, I basically need two new tools that would allow me to basically split the streams. Then I can decode, and then I need to combine those frames to form the alpha. So the first element I had to write is CodecAlphaDemax. It was a simple element. It would have one input stream. It would read from the input the GST video codec alpha meta. It would remove the codec alpha field from the caps, and then it would push everything toward two pads. So there's the color, the base pad, which is the colors, and then it would push the GST buffer from the codec alpha meta on the alpha pad, and that's it. Now you have two streams that you can put into queues, run into decoders, and get two parallel decoder running. Now, out of the decoders, now we have two decoders running on their own threads, so there's a bit more of a challenge when it comes times to combine the alpha. So I ended up implementing AlphaCombine as a fairly simple element in the sense that it doesn't do time synchronization or timeout like an aggregator would do, because I thought it was a bit of an overhead to introduce yet another thread in this case. And because we know that there's always going to be one frame for one alpha frame for all color frames. And in fact, if there's one missing, we can actually signal it with a gap. We have gap mechanism in GStreamer for that. So we'll wait until the color and the alpha buffer are ready. Then we would append the memory together. You have to know that GST buffers are containers for GST memory. GST memory are blocks of data. And we basically represent a virtual single memory group. So it doesn't matter if your data is one GST buffer or multiple GST buffer, except there's some restriction. You cannot have multiple GST memory for the same plane in GStreamer. It should be the same. And then I can just append them together and ignore the UV, and then I get a new format. Fortunately for the software decoder, the decoder produced I420, which is exactly what I described at the beginning, 3 separate planes. And then I would transform this in an already supported format called A420, which is the same format, but at the end, there's an alpha plane that is added, exactly what we needed. The beauty of AlphaCombine is that despite its name, it's actually not doing any binary operations. So it's totally zero copy. It's just a pure symbolic manipulation of the memory inside the GStreamer system. Now, that's great, but part of my work was to support hardware decoders. And to be honest, today's hardware decoder, they will all support NV12 or some variation of it. So in NV12, the format is basically okay, but the format of NV12 is not that different. It keeps the luma, the brightness, actually separate, and it will interleave the U and the V in the same buffer. So that basically means we could do exactly the same thing if such a format existed. But the truth is that I didn't find any such format, but that didn't really block me. So, I mean, first time in 10 years, I decided to create my own format. So I created AV12. Arguably, I think I found some people that might be using that on some proprietary tool. So I might not be the creator, but anyway, it's the first made-up format I added to GStreamer, and that serves very well the purpose. So it's exactly that. It's NV12, and then you can add an extra alpha format at the end in order to carry the alpha. And you ignore the UV plane. And they have the same features that when you set the UV, you want to set them to a uniform value in order to compress very well. So in the end, we added a bunch of elements into GStreamer. So there's a new plugin called CodecAlpha, which have the helpers, the helpers I mentioned. And then to make all this works, we actually need decoders. So actually we need bins. So we need a container that will actually abstract the graph I've showed earlier. And I ended up exposing some decoders. So there's VP8 Alpha decode bin and VP9 Alpha decode bin. And these are strictly used to decode WebM Alpha with software decoders. And then for the V4L2SL VPL Alpha decode bin, it's very long. V4L2SL, just a side note, SL is for stateless. It's a new kernel API to support decoding with hardware that is called to be stateless, which doesn't actually do the parsing and the state management for your codecs. This is something I've been working on outside of GStreamer a lot on these APIs and reviewing these API upstream. So this is also another subject I work on. And we wanted to support these. Of course, we can add as many wrappers as we need, as long as we have the ability to do the zero-copy AlphaCombine, or another means, so some tool that would allow this in the context. I prepared a couple of demos actually of this. So this is basically, I thought it was much more interesting to see what these things do. I just want to mention before we actually start the demo that I'm streaming, I'm doing some encoding over the internet, and my little laptop may suffer a little bit. It's very warm. So some of the demo that worked great before the presentation actually can stutter a little bit. I noticed this during my tech check. So let's start with the first demo, how that works. First thing, let's check what we have new. So I said we have a new CodecAlpha plugin. So you can see that's GStInspect, that we have the new AlphaCombine element, the new CodecAlphaDemax element, and then we have the 2 decode bin. And then if, I won't see the V4L one on my laptop because I don't have such hardware in there. And if I look into, let's say, VP9 Alpha decode bin, you can see that, let's start from here. You can see that we have a codec decoder that is for video. It's a wrapper bin for VP9. You can see his rank. So one of the issue we had with was that due to how the autoplugger compared the capabilities in order to determine what is a fit and what is not a fit, and the fact that we use the same media type, the easiest way to make the alpha decoder work was basically to limit their use to alpha decoding, so they don't support standard VP9, and make their rank. So rank is just to order basically the list of element when it comes times to autoplug to something higher. So it's primary plus 10 in this case. And then if it was a hardware wrapper bin, it would be a little higher again. So that's just made so it's higher any VP9 implementation, and it would be looked at first or discarded by the autoplugger. And then there's not much property. It's all the default stuff, but you can see all the child elements, the combiner, the decoders, the queues, and the CodecAlphaDemax in there. Now, how do you play this? Let's take a stinger, because we talk about stinger. So here, we're going to use a little terminal player, command line player. I'm going to use Plebin3 because it's generally work better for this type of application. And this is a stinger I've downloaded on the internet that was available for free. I just forgot where it is from, but thanks for this. So let's play this demo. Will it play? Oh, it did play in the background. There we go. So when I'm screen sharing, I discovered that window don't pops over; they actually stay behind. So I need to remember. So that's what it looked like. You can see that. Oh, I'm missing a bit of it. You can see that initially it's transparent. Oops, and then it goes away. Pretty hard to catch, right? Let's seek to 0. Put the window in the front. There we go. Hope you saw it. So that's using basically, I'm basically using the player, and I'm using GL image sync, and I'm telling the display sync to avoid ignoring the alpha channel, so you can see through the window. Now, Stinger is not the only thing we could play. There's also this is about transparent videos in general, so you can play all kind of content. So I created an overlay demo, which I found, which I'll show you on the web also later. And in this case, we're just playing a different movie. So let's run demo overlay. There we go. This one stuttered a little bit, but you got a phone actually that is going around on top of my desktop, and it's all semi-transparent. And one of the surprise, I kind of thought it would help, but I didn't know it was going to just work. So this effort also helped the Webkit community in order to fill in some of the gap in some of the missing feature, because browsers are mandated to support these streams, but GStreamer-based Webkit implementation didn't support that yet. So that's helping Webkit GTK and Webkit WPE. And I'll show you what it looked like before, actually, before my changes. Here we go. So it's going to be a bit stuttery, but basically you had the phone going around. It's a website, and you had the phone going around and a black background. So it's clearly not the appropriate render for this web page. So for them, it was actually some test failure. Let me show you how I was running this. So demo Epiphany before. So basically, I've used one of the new feature which allow you to adjust the rank of element using an environment. And I've disabled VP9 alpha decode bin, so it was no longer visible to Epiphany, which is an auto, well, to WebKit, which is using an auto plugger to choose the element. And then I'm visiting this web page over here. Now let's do the same, but we're not going to disable the alpha decoder, the other one. There we go. So I was really surprised. I was really impressed. When I was done, when it was all debugged and everything, I just launched Epiphany, the GNOME web browser, and it literally just worked. There was a little problem around the edge of that phone because there's a gradient of semi-transparency, and they had mishandling of the pre-multiplied alpha in this case, because videos are straight. We say straight, so they have full color information and the alpha. While in rendering, usually you want to pre-multiply the color as soon as possible, because if you're going to render the same object, it's much faster to do the blending. It optimizes the blending. You also want to do this for scaling purpose. But as they never tested it, it was quite expected to have small little bugs. But they fixed it basically the same day I've published the code. So thanks to Igalia crew who did all this nice work. Now, as I said, I needed to support hardware acceleration. And hardware I'm going to show you today, I'm not going to be able to show it to the camera. There's too many wires there. So I'm going to unplug it if I do that. It's actually a Renegade Elite from LibreComputer. It actually hosts a Rockchip RK3399. It's a chip that has been very popular from, I would say, 2015, 2019 on Chromebooks, ARM Chromebooks. It's pretty powerful. Our target was RK3566, but that's too early samples and too unstable for me to show you. So what I'm going to do to be able to show you that, I'm going to use another GStreamer pipeline. So it's the RK33 viewer here, which actually runs a V4L2 source because it's a UVC camera. And I just select the format because my little capture box likes to convert, and then I'll send it to GLImageInc. So this should, if it works, now we're on target, display Weston. Oh, it's in the background. Okay, there we go. So now we have Weston. I need a terminal to actually launch a demo there. So I'm actually on the device. I've cross-built GStreamer on my machine, and I can show you how, but in my GStreamer 3, I'm running a script called gst-env. I just ask to strip off the path from my NFS export. And this way, I don't need to install GStreamer every time I make a modification. So it's my development environment on target. It's a bit slow to load over NFS. There's a lot of files to look at, but it works. Then I'll go to the demo folder. I wanted to show you the same demos, but turns out my OS on this target is too old. So I got a too old Mesa with too old Panfrost, too old everything, basically, to show you the browser running. But be aware, this is all mainline Linux. It's a 516 RC something with stock Mesa running from Fedora, and it's quite good. It's quite good. I'm quite impressed these days of what you can do with just open source, just mainline tool. So the demo that works actually, and that I'm going to show you, is the overlay, the little overlay phone that's been. There we go. So it's starting. There we go. So we're on RK3399. We got a hardware accelerated VP9 alpha transform. One of the things that you have to consider when you want to use hardware acceleration on these is that in order to decode this stream, which is just a simple 30 FPS VP9 video, it's 1080p, I need 60 FPS power in my hardware in order to do that, because I need to decode 2 concurrent streams. And my system need to be well optimized. If you want to go in streaming standards and go to 60 FPS, you need a 120 FPS decoder in order to do that. And if you're streaming in 4K, that could effectively be a challenge to find hardware, even laptops that supports that. You probably need a big GPU to actually handle it. But keeping that in mind, there's always a way to do that. There we go. I'm quite impressed, but be aware that the VP9 decoder on that platform is 4K 60 capable. So having 60 FPS 1080p should be fine. And voila, that's it for my demos. Now, okay, let me keep there we go. So like everything else, it's quite rare that we manage to do all the feature we would like in a Go, especially when they're not sponsored. But there's many addition that could be done. So if you want to contribute or you want to encourage some contributions, feel free to express your needs. One of the things I looked at is what other hardware accelerator could be used to do that. I got from okay, so I got that it should be fairly easy with Direct3D 11 decoders to do that, and and version 12 also. It's just about someone to do it. About VA API, it looks like we need some more infrastructure around DRM pixel format with the modifiers and all these things in place before we can actually do something that is truly efficient. Because even though they do NV12, they do bit of a variation of NV12. So the decoder would produce NV12, but the data is actually whether compressed, tiled, or something which is specific and undocumented. Well, not really undocumented, but it's specific, let's say, to Intel or AMD. And we need to carry that modifier, that extra representation, till we get to the GPU in order to process and color convert the YUV to RGB, the data. So until we have this infrastructure in place, it's going to be hard. But I think as soon as this is in place, the wrapper shouldn't be much more complex than what we have for software decoder and the V4L decoder. I forgot to list it, but I also I basically forgot to do that. I will probably do that in the next weeks before release. But I forgot the V4L stateful decoders, which also have VP8 and VP9 support. We're also missing the Apple codec support that would be used on iOS and OS X. And we're entirely missing the encoding and muxing. So in order to encode, though, there was a discussion ongoing on the issue tracker, which has been very useful. And we believe that we need basically the reverse tool. So we need an alpha split that would actually take an AYUV or an AV12 buffer and make two NV12 or two I420 buffers. And we would need the CodecAlphaDemax, which would basically attach the alpha GST buffer on the GST buffer of the colors. And finally, we would need to mux it. I believe that muxing will be much easier, basically. We will know ahead of time from the caps that we need to add the alpha the alpha tag in the segment. So that's a very good fit. And then we just need to pick the GST meta and wrap it as a block addition in the stream. So that should be very straightforward, I believe. Oops, no focus. Voila. Well, that's pretty good. So thank you. That was it. And we're ready for the questions.
Excellent. Hello, I'm back.
Oh, I need to put my headset, sorry.
Oh, yeah, you do. Welcome back.
I'm back.
We've got some good questions. That was a really interesting talk. Thank you so much for that, Nicolas.
Thanks.
The first question that we're going to go for is, do the resolutions have to match on the main stream and the alpha stream? Could you use a lower resolution on the alpha stream and upscale?
Right now, they must match in this. It's actually defined by the WebM Alpha specification. And it would also be a limitation because AlphaCombine, the element that actually takes the two streams and combine them, assume that they actually match. So we don't have metadata to describe an alpha plane, which would be a bit sampled, I would say, if it was like a half of a fourth of the plane. So yes, they need to match.
Okay, and we've got a very similar question as well. Likewise, do the frame rates have to match on the main and alpha streams? Could you use a lower frame rate for the alpha stream and interpolate at playback?
So the spec is incomplete. It doesn't define everything. But when you look at the streams being produced, the rules are the following. You need your first frame to have an alpha frame. That's mandatory. So when you start, you need to provide the initial data for your alpha, even if it's fully transparent. And this is to satisfy hardware decoders, basically, because they need special buffers. And crafting those buffers with a CPU is it's slow, so it would just delay the start and increase your latency. And then you're allowed to skip the alpha channel anytime actually the data does not change. That being said, it's a lot of effort for very low gain, because the VP, something you need to know about the VPX bitstream, which is from On2. It was highly patented before it was released by Google, so thanks for that. It's probably the best compressed bitstream out there. It actually do some statistics on the previous decoded frame in order to better compress your parameters. So if a parameter is always the same value, it's going to use less bits. And if you have like the same frame, it actually can go up to just a couple of bytes to say, please just render a previous frame. That's part of the codecs in VP8 and VP9. This is a very powerful feature. So usually it gets so small, just a couple of bytes, that it's probably too much effort to do that. But you can, yes. there's no problem with that.
That's real cool. I think that is all the questions that we've got in chat for now. Yep, it is.
I must admit, this was an excellent question. Thank you.
Yeah, that's really cool to know, though. The encoding, like, that's really interesting. Thank you so much for coming and talking to us. This was a really interesting talk about some stuff that I don't often hear about, which is really cool.
I'll just mention one thing I had to do. There's job opening at Collabora, so if you're looking for a new opportunity, please visit call.la/careers. If you find something that suits you, you can contact directly or one of us. If you know one of us, we're everywhere on IRC, on Slack, on wherever. We're pretty much all over the place. Thank you.
Cool. Thank you so much.
Have a nice day.
Our next talk in this room is the Let's Make a Game with Paris Botfield Addison, and that's at 11:40 a.m. ADTT. So that's in like 15 minutes, if I can do maths correctly.
Let's not miss that. Great.
I'll see you later. Thank you very much.
Bye-bye.